Now, you might know from a grade school geometry class that the volume of a pyramid is 1/3 times the area of the base times the height. Or perhaps more famously, the volume of a cone is 1/3 times pi r squared times the height. But where do these formulas come from? We can derive them using calculus, which we'll get to shortly, but Newton and Leibniz didn't develop calculus until the late 17th century, which is curious because the ancient Egyptians built the Great Pyramids of Giza around 2500 BC, and records show that they had formulas for how to calculate the volume of a pyramid. Let's take a closer look. Shown to the right of the screen, there's an animation of a pyramid in Desmos. The base is a square of side length 2 and the height is 3. Using our known formula, first of all, the area of the base of a square is just 2 squared, so the base is 4. So therefore, the volume of our pyramid, remember that the height was 3, is 1/3 times 4 times 3, which we know is just 4. As mentioned previously, we can prove that this formula truly works by using calculus. By dividing the pyramid into infinitely small cross-sectional areas and adding up the volume of each teeny tiny piece, as you can see in the animation to the right, we get the total volume of the pyramid. This summation of infinite areas can be represented by an integral of the function of area with respect to our position on the z-axis. Consider this right triangle. This right triangle is a side view of our pyramid, and we're only looking at the right half of it for now because we want to get a right triangle. So this length right here is the height of our pyramid. Since we're only looking at the right half for now, this is half the side length of the base of our triangle. So for our cross-sectional squares, we're going to come down from the top a distance z. So we need to know what this length is right here to figure out the area of a cross-sectional square. So geometry tells us that the proportion of this smaller length to the full length is equal to this smaller length to the full length. So we can write that in the following formula. Z over H is equal to half of our L over half of our S. Now, of course, the halves can cancel, so we get Z over H equals L over S. But what we're really interested in is the length L right here, because we want to find the area of the cross-sectional square, which we need the side length for. So finally, we'll multiply by S to get our final formula. L equals ZS over H. So now we're ready to evaluate the integral. A of z represents the area of our infinitely thin cross-sectional square. We know the area of a square to be the side length squared, and we just calculated the value of the side length of this cross-section. We set L equaled z times s over h, where z is the distance from the cross-section to the top of the pyramid, s is the side length of the pyramid's base, and h is its height. So we now have A of z equals L squared, which equals z times s over h all squared. So we can rewrite this integral as integral from 0 to h of, I'm going to rewrite this piece as s squared over h squared, and that's times z squared dz. Notice that s squared is the area of the base of our pyramid. So s is the side length, s squared is the area of the base. So we can rewrite that as b. 0 to h v over h squared times z squared dz. So last step, our integral rules tell us that we need to bump up the power on the z and divide it out front. So we have 1/3 v over h squared times z cubed, and that needs to be evaluated from 0 to h, because those are our limits of integration. So first we'll plug in h for z. We get 1/3 v over h squared times h cubed, and then we subtract when we plug in the lower limit of integration. So if we plug in 0 for z, we're going to get this whole thing times 0. So really this is all just minus 0. And notice we get some h's that cancel. So this whole formula is going to end up equaling 1/3 times the base times the height, which is our familiar formula from grade school. The ancient Egyptians did know this relationship, but they didn't teach their math in explicit formulas. Instead, they used an examples-first approach. Recall our pyramid from before. They would have expressed it something like this. Take 2 and square it. Then multiply by 1/3 of 3. See, it is 4. You have found it correctly. The Egyptians had enough confidence to declare that their answers to geometry problems were correct, but we never see an actual proof anywhere in their work. How could they have known we need to multiply by 1/3? Well, the truth is, nobody really knows for sure. But if you look closely at this photo of the famous pyramids, you can see each individual layer of stones. Although they were not able to sum infinitely small layers like we just demonstrated, they could have gotten a pretty close estimate of volume by adding the volume of many layers of the pyramid. It is also quite possible that they recognized this 1/3 factor experimentally. A clay mold of a rectangular prism required triple the amount of clay than a pyramid of the same base and height. Or maybe a pyramid-shaped container full of water could fill a rectangular prism-shaped container after 3 pours. Still another theory is that they had a proof, but the Greeks credited this work to themselves, and we no longer have documentation of this proof from the Egyptians. A characteristic of ancient Egyptian math was their vague distinction between the exact and the approximate. Because of this, I believe that experience led them to the formula with the 1/3 factor, and they never had to question it because it always worked in their calculations. However they came up with their math, it is truly remarkable that they were able to discover so much and pass it all down from generation to generation, and that they were so well organized to build the famous pyramids. Thank you so much for watching. Please like and subscribe to stay notified for the next video in which we will analyze the math of ancient Greece.